Alright, so let's get started. In this video, we are going to talk about rotation. We have talked about various aspects of rotation in previous chapters. So we've talked about rotation a little bit in chapter 3. We've talked about it in chapter 5. So some of the things that you're going to learn about in this chapter will seem familiar because you've heard about them before. Alright, so now the first thing that we're going to discuss when we talk about rotation is the concept of the axis of rotation. So the axis is exactly what you think it is. It is an imaginary line about which the whole system is rotating. For example, if you have a bicycle wheel like in this picture here, the axis of rotation would be an imaginary line which passes through the center of the wheel and is perpendicular to the wheel. If you have a globe that's rotating, then the axis would be an imaginary line that passes through the north and the south poles. So the axis is nothing but an imaginary line about which the system rotates. Okay, now if an object is rotating, suppose you have an object that's going in a circle like this. If it's going in a circle, the radius is always fixed. So the only thing that you need to keep track of is the angle that the object is making with respect to some reference direction. So suppose our reference direction is the x-axis and the object is over here. Then we only need to keep track of this angle. Right? So this angle that the object makes, that the radius vector of the object makes with respect to some arbitrary reference direction is called the angular, angular position. So theta here is our angular position. Now, suppose the object was initially at the angle theta 0, and then it moves to a new angle theta. So what is the change in its angular position? The change in its angular position is this angle right here, and we're going to call that delta theta. So delta theta is called the angular displacement. So theta is the angular position and delta theta is the angular displacement. Remember when we talked about position and displacement in earlier chapters, the displacement was just the change in position, the final position minus the initial position. So here it's exactly the same thing. Delta theta is the angular displacement, and that is just theta final minus theta initial. All right. The next thing is the distance moved by an object as it's moving along a circular path. So suppose the object starts over here at point A and then it moves to point B. Its angular position has changed by an amount delta theta, right? How much distance has it covered along the arc of the circle? So what is this distance going to be? So we're going to call this distance delta S and let the radius of the circle be r. So if you know r and delta theta, what is delta S? The answer is delta S is given by r delta theta. And you might have seen this formula before. It is just the arc length formula. You might have seen it in the form S equals r theta, which is sometimes called the arc length formula. So we are basically just using the arc length formula, except that we are calling the angle as delta theta and the distance, the arc length, as delta S. Okay, now suppose the object moves through a very, very tiny angle. So suppose the object is, all right, so I'll just draw a different one. Suppose this is our circular path and the object was initially over here at an angle theta, and then it changes its angle by a very, very tiny amount. So let this angle be called d theta, right? So you know that a very tiny change to a variable in calculus, we just call that d of that variable. So d theta means a very, very tiny change to theta, right? So how much, so what is the change in the, what is the distance moved by the object? So we're going to call this infinitesimally small distance as ds, right? And so what's the relationship between r d theta and ds? Using the same formula as before, ds is going to be r d theta. Okay, now ds is equal to r d theta. All right, so at the bottom of the PowerPoint slide, slide 3 of the PowerPoint, there's a question, what is the direction of ds? Now, going back to this diagram, the previous one, if I had asked you what is the direction of delta s, you would say that delta s is not a straight line, so there is no direction for delta s, right? It's a curved line. But if I ask you what is the direction of ds, then if you think about it, ds does have a direction. Why? Because I told you that the angle d theta is extremely, extremely small. So that means the two ends of ds are extremely close to one another, right? So on 2 points which are infinitesimally close to one another lie on the tangent to the circle, right? So that's pretty much the definition of the tangent. So ds is along in the tangential direction, right? So you can draw a tangent over here. You have to remember that ds is extremely small. The two ends of ds are practically next to one another. So the direction of the vector ds, you can think of ds as a vector, and its direction would be in the tangential direction, right? So ds is in the tangential direction. Okay. All right, but the same could not be said for a finite displacement of a finite angle delta theta. In that case, the arc length would actually be curved, and so it would not have any particular direction. This is only when the angle is subtended by the arc d theta is extremely small. Then you can think of it as being in the tangential direction. All right, now I'll talk a little bit about the arc length formula in case some of you might not be familiar with it or might have forgotten it. So this is a little aside on the arc length formula. So we say that S, the arc length, is equal to r theta. Oops, I should draw it over here. Okay, so S is equal to r theta. Now, in this formula, you should always remember that theta has to be in radians. If you use degrees for theta, you're going to get the wrong answer. So theta has to be in radians, right? And radians are unitless. They're pure numbers, right? Okay. So let's look at one example. So suppose theta, before we do that, suppose this is a circular track. The diagram that I have here is a circular track, and you start at this point A, right? And let's say that the radius of this circle is 3 meters. Okay, so r is 3 meters. Now suppose you start walking from A, and you walk a distance which is exactly equal to 3 meters. So you along the circle, you cover a distance which is exactly equal to the radius of the circle, right? So you start walking, you have a pedometer, and you keep walking until your pedometer says that you've walked 3 meters, the same distance as the radius of the circle. So in that case, S is equal to R, right? And from the arc length formula, if S is equal to R, that would mean theta is equal to 1 radian. And that is pretty much the definition of a radian. So A radian is the angle subtended by an arc which is equal in length to the radius of the circle. So 1 radian is the angle subtended by an arc that is equal to the radius of the circle. Okay, that's the definition of a radian. And 1 radian is approximately 57.3 degrees, I think. All right. There is one other thing I can show you here. So suppose you start at A and you keep going all the way until you get back to A again. So you walk one full circle around the track. So you go around the track full circle. So what is the angle that you've traced out? So in that case, so if you do a full circle, the angle that you've traced out, theta, is equal to 2 pi, right? So what is the arc length that you've traced out? So S is equal to r times theta. So that's 2 pi multiplied by r. And that's exactly what you would expect. You get the circumference of the circle, formula for the circumference of the circle. Okay? So that's another example of applying this formula. All right. Now, on slide 4, I have a problem which is just an application of the arc length formula. Let's try the problem on slide 6. All right. So what this problem is saying is that you're given the angular diameter of the moon. The angular diameter is a very common term in astronomy. What does it mean? So somebody's watching the moon from over here, and there is the moon up here in the sky. The angular diameter would mean that you draw a straight line from the person's eye to one end of the moon, and another straight line from the person's eye to the other end of the moon, right? The angle between these two straight lines is called the angular diameter. Let's call it theta. And so theta is given to be 0.52 degrees in the problem. This angle is the angular diameter. Okay, so you're given the angular diameter and you're also given the distance to the moon. So the distance to the moon is 380,000 kilometers. And using these two pieces of information, you have to find out the physical diameter of the moon, right? Okay, now one thing that you can do is you could use the arc length formula to find the length of the arc between the two ends of the two opposite sides of the moon. So the length of the arc would kind of look like this. Now, since this angle theta is extremely small, if you think about it, there won't be that much difference between the arc length and the straight line length between the two ends of the moon. So let me just call the two ends of the moon A and B. So if you think about it carefully, there's not that much of a difference between the arc AB and the straight line joining A and B, right? So if theta is small, then the arc AB is pretty much the same, is approximately the same as the actual distance connecting the points A and B, which is the diameter of the moon, right? A straight line distance between A and B, which is the diameter of the moon. So in that case, we could just use the arc length and call that the physical diameter of the moon, right? Arc length is very easy to find. S equals r theta. So r is 380,000 kilometers. Theta we have to express in radians. So to convert between degrees and radians, you use the fact that pi radians is 180 degrees, right? So that means 0.52 degrees would be 0.52 multiplied by pi divided by 180 degrees. And if you work this out, so you get 3,449 approximately kilometers, which is a fairly good value for the diameter, fairly accurate value for the diameter of the moon, the physical diameter of the moon. All right, okay. So the next thing that we're going to talk about is angular velocity. So we were talking about an object that's moving in a circular path, and we talked about the angular displacement. So let's say that the object was initially over here, and then it moves over here and traces out this angle delta theta, right? Suppose this angle changes by delta theta in time delta t, right? Angular velocity measures how fast this angle at the center is changing, right? So the units of angular velocity are radians per second. So if the object changes its angle at the center by an amount delta theta in time delta t, you can define an average angular velocity, and the symbol for angular velocity is omega. This is the Greek lowercase w. So omega average is defined as delta theta divided by delta t. Right. Now, you know that we are not that interested in average quantities in this course. We are far more interested in instantaneous quantities. So I might want to know what is the omega at maybe t equals 5 seconds, or what is the omega at t equals 7 seconds. So in that case, what you do is you calculate the same thing, delta theta divided by delta t, but you make the delta t as tiny as possible. So if you want to know what is omega at t equals 5 seconds, then you want to consider a delta t, which is very close to 5, like which goes from 4.999 to 5.001, something like that. So the instantaneous angular velocity, which is what we are far more interested in, is the limit delta t going to 0, delta theta divided by delta t. And as you know from calculus, this is nothing but d theta dt. This is the definition of the derivative. So it's d theta dt. So this concept of instantaneous omega is very similar to the concept of instantaneous velocity that we talked about a long time ago back in chapter 2. So we get this very important relationship that omega is just d theta dt, the rate of change of angular position. Right? If the units of omega would be radians per second, right? And those are the units that we'll be using most of the time. If omega is constant, that is what we call uniform circular motion. So constant omega is uniform circular motion. So we had talked about omega briefly a long time ago, back in chapter 3, when we were doing a problem involving a vector problem involving rotational motion. And so we had talked about it at that time. And if you remember, I pointed out that omega measures how quickly the central angle is changing. And you can see that over here too. So that's exactly what it does. Omega is d theta dt. All right. Now, you might be surprised to learn that omega is actually a vector. You might have thought that it's a scalar, but it's actually a vector and it has a direction. So what is the direction of omega? So to find the direction of omega, what you do is, let's get rid of this. So to find the direction of omega, you use the right-hand rule. How does the right-hand rule work? So you curl the fingers of your right hand in the way that's shown in the diagram. And then you, okay, just one second. Yeah, you curl the fingers of your right hand the way it's shown in the diagram over here. And then your thumb will point in the direction of omega. So for example, if you curl the fingers of your right hand um, in this direction, then your thumb, you'll find, is pointing in the direction of the arrow shown, right? I can show you another example. Suppose an object is moving in a circle like this, right, in the counterclockwise direction. So if you curl the fingers of your right hand in the counterclockwise direction, you'll see that your thumb is pointed out of the page, right? And so that is the direction of omega in this case. So omega would be out of the page in this example. And if an object is moving in the clockwise direction, then omega would be into the page. Let's look at another example. Suppose you have somebody riding a bicycle. So here is our bicycle, and let's say that the person is moving in this direction. So that means the wheels of the bicycle are turning like this. What is the direction of omega of the wheels of the bicycle? So the way you would do it is you would curl the fingers of your right hand in the same direction in which the wheels are turning, right? And so the wheels are turning counterclockwise in this example. So that means the direction of omega is out of the page. And so the direction of omega would be to the left of the person riding the bicycle, right? So omega would point to the left of the cyclist.